Today we want to talk a little bit about how we can decompose stresses into hydrostatic and deviatoric components and why we might want to do that. We'll talk more about it when we enter our formal plasticity section, but this is a little bit of a preview of that. Let's just begin by saying that the stress tensor, so sigma, can be decomposed into what's called into a hydrostatic, or sometimes this is just called a spherical, because it's the same in all directions. It basically is a pressure component, and a deviatoric component. Okay, so the key here is that it's decomposed into basically a pressure, and that's going to be the same in all directions. And this is going to be decomposed into stresses not related to a pressure. Okay, and we typically think of these as shear components. So under a pure pressure loading, there is no deviatoric component. Under a pure shear loading, there's no hydrostatic component. Okay? So the decomposition is actually very simple. We just say that the stress tensor sigma can be decomposed into a deviatoric stress plus a hydrostatic stress, which we'll just call sigma m times I, right? So it's a equal stress in each of the three directions. So this is the spherical or hydrostatic component, and this is the deviatoric stress. Okay, and so where we can just define them fairly easily, where sigma m and above is just 1/3 of the trace. So this is basically the mean normal stress or the pressure. So it's 1/3 of the trace of the stress tensor, and we can easily also define the deviatoric component S just by rearranging that equation above and saying it's the stress tensor minus sigma m times I. If you like that in index notation, that means it's sigma ij minus 1/3 sigma kk times delta ij. So why do we decompose them like this? What's the point? Why decompose like this? Well, if you've taken any sort of a materials course, hopefully you remember that, let's say in the case of metals, that plastic deformation typically occurs via the glide of dislocations. And hopefully in that class you learned that dislocations only glide in response to a shear stress. So the hydrostatic component doesn't play any role in the plastic deformation of the metal. And so when we're developing theories for these things, we would like to only treat the components that actually make a difference with respect to the physics that we're interested in. So why do we decompose like this? Because hydrostatic stresses typically don't cause plasticity. So if we're going to work with deviatoric stresses, it's worth asking what relationship did those bear to the stresses we just computed. So if you remember, we've just got done talking about principal stresses, and so we want to see how do maybe the principal directions of the deviatoric stress tensor match up with the principal directions of the original stress tensor, or the complete stress tensor. So let's go ahead and look at the relationship between the stress tensor sigma and the deviatoric stress tensor S in terms of principal directions. Okay, and the reason that we're interested in doing this is because because we want to be able to use, if we can say something about, let's say, a principal stress, we'd like to be able to know that that principal stress is valid in a deviatoric reference as well. So let's think about this. Let's remember here that by definition, we could write we wrote previously that sigma ij minus sigma q, and then sigma q is one of the principal stresses, so sigma 1, sigma 2, or sigma 3, times delta ij times nj is equal to 0. That was our classic eigenvalue problem, and this is a principal stress. So if that's our definition, and we just plug in our definition of the deviatoric stress tensor, we can write that, remember, sigma ij is equal to Sij plus sigma m times delta ij. So that's the sigma ij component. And we go minus sigma q times delta ij. That quantity times nj is equal to 0. If we do some simplification, that looks like sigma ij minus sigma q minus sigma m delta ij nj is equal to 0. And we can just define this quantity, sigma q, which is the principal stress 1, 2, or 3, minus the mean stress, which is 1/3 of the trace, and we can call that SQ. And so then we can finally write Sij minus SQ delta ij times nj equals 0. Now, why do we do that? Well, what we see is that the same, we didn't change n. So the n that was the solution to the principal stress problem right up in here is the same n that would be the solution to this eigenvalue problem. And so what we've basically shown is that the principal directions of the original stress tensor are the principal directions of the deviatoric stress tensor. So let me write that out. So therefore, since nj is the same for the eigenvalues of sigma and the eigenvalues of s, the principal directions of s and sigma are the same. Okay, a couple things I'd like to note, though, is that this is just as a way of reminding you. So when we solved this problem, the eigenvalue problem with just stress, we were looking at, remember, we were extremizing the normal stress. So sigma 1, sigma 2, sigma 3, those sigma q values, those represent the stationary points of the stress tensor. So the max, the saddle basically, and then the minimum of the stress tensor. In contrast, just be aware that SQ, we didn't solve for that way. All we said was that it was an eigenvalue that satisfied this problem. So SQ is the principal deviatoric stress, but it's not the maximum shear stress or deviatoric stress. Sorry, it's just, yeah. Okay, because we didn't set it up to be that way. So I want to move a little bit further because I want to show you why we care about this deviatoric stress tensor. And hopefully you remember back from your undergraduate career that frequently when you were investigating failure of materials, you were looking at some form of a stress. Maybe it was the max stress, but oftentimes, at least in engineering design, we look at the von Mises stress. And I wanted to show you how the deviatoric stress tensor is related to the von Mises stress and why there's a linkage. And this is just a little bit of a preview because we're going to go, when we start talking about plasticity theories, we'll go back and explore this a little further, but this is just kind of to whet your appetite as to why it's important. So first off, since I can use the same principal directions as my stress tensor has, I'm going to go ahead and consider my deviatoric stress tensor, S, in its principal directions. And this is oftentimes the kind of thing that we like to do because it makes life easier for us. Okay, so that means I could write in matrix form that S looks like S1, S2, and S3 with zeros everywhere else. Okay. And so let's go ahead and look at the invariance. So when we talk about invariance with the deviatoric stress tensor, we denote those invariants with the letter J. So remember, with stress invariance of the full stress tensor, we denoted them with I. For the invariance with the deviatoric stress tensor, we denote with J. So J1 is going to be equal to SII, the trace, right? So let's think about what that looks like. Well, we're going to go back to the definition of our deviatoric stress. That's going to be sigma II minus 1/3 sigma kk times delta II. Okay? So hopefully you remember from homework that delta II is going to be equal to 3. 3 times 1/3 is going to be just 1. And so I end up with sigma II minus sigma kk. Those are just dummy indices. And this comes out to be identically 0. Okay? Similarly, we can look at J3, and it's this, instead of being the determinant of sigma, it's just going to be the determinant of S. And we could write that similarly as epsilon ijk times, let's see, SI1, SJ2, SK3, which if we do all this out, looks like S1 times S2 times S3. Okay, I'm not going to focus too much on those two quantities, but I do want to look at J2. So for J2, I write that as 1/2 times Sij minus Sii Sjj, but we just showed up here that Sii was 0, so this quantity goes away to 0, and I'm left with 1/2 times Sij times Sij. Okay, which looks like, if I go back up to my deviatoric stress written in principal directions, this just looks like 1/2 times S1 squared plus S2 squared plus S3 squared. Okay? So, let's think about what each of those looks like. So let's just say, but S1, we defined already above, looks like sigma 1 minus sigma m, and then S2 is equal to sigma 2 minus sigma m, and then S3 is equal to sigma 3 minus sigma m. Okay, so now I want to just expand out sigma m, and then I'm going to do a little rearranging. So let's just say, so the relevant quantity that I care about is, I want to know what is S1 squared plus S2 squared plus S3 squared looks like. And if I take these quantities here and substitute them into that equation, I end up with something that looks like sigma 1 squared plus sigma 2 squared plus sigma 3 squared minus 3 times sigma m squared. Okay, so now I'm going to go ahead and expand sigma m and rearranging, okay, and I end up with being able to write that S1 squared plus S2 squared plus S3 squared is going to be equal to sigma 1 squared plus sigma 2 squared plus sigma 3 squared minus, so remember what sigma m looked like. Sigma m looked like 1/3 sigma kk, but if we're in the principal coordinate system, that looks like sigma 1 plus sigma 2 plus sigma 3. So if I take that quantity squared, I end up with 1/9 times this quantity squared times 3, which just gives me 1/3 again, times this quantity, sigma 1 plus sigma 2 plus sigma 3, the quantity squared. Okay, and I can then just start simplifying this algebraically. Obviously, I have, if I go ahead and carry this squared out here and then combine it with these terms, you'll see I get at least a sigma I squared times 1/3 subtracted off a sigma I squared, so there's a 2/3 that comes out of there. In fact, if you expand it all out, and I encourage you to do so just to convince yourself this is all true, I end up with 2/3 times sigma 1 squared plus sigma 2 squared plus sigma 3 squared. Whoops. Let's make that actually a 3. Sigma 3 squared. And then I have these other off terms, minus sigma 1 sigma 2 minus sigma 1 sigma 3 minus sigma 2 sigma 3. Okay? Now, this is one of those moments where you're going to wish that you felt more comfortable with your algebra. But hopefully you're kind of able to, by this stage in your career, look at something like this and say, I think that there's maybe a way to rearrange this in something that's a little bit more convenient. And there is. So how we're going to write this is we're going to say, well, we'll have this 2/3 still out here. But what if I write this as 1/2 times sigma 1 squared plus, oops, sorry, not a plus, minus, I pulled a 1/2 out, so I actually need to write it as a 2 times sigma 1 times sigma 2 plus sigma 2 squared. And then I have another term that looks like plus sigma 2 squared minus 2 times sigma 2 sigma 3 plus sigma 3 squared, and then plus 1/2 times sigma 1 squared minus 2 sigma 1 sigma 3. I don't know why I can't draw 3. Plus sigma 3 squared. Okay? And hopefully you can see that we didn't do anything except just simply rearrange the terms a little bit. We didn't do anything that was too tricky there. But now I hope you see that this is a difference of squares. This is sigma 1 minus sigma 2, the quantity squared, and each of these has a half in front of it, so I can multiply that half or factor that half out. It cancels out with this 2, and I'm left with 1/3 times the quantity sigma 1 minus sigma 2, the quantity squared, plus sigma 2 minus sigma 3, the quantity squared, plus sigma 1 minus sigma 3, the quantity squared. Okay? So and now I'm able to write J2. So I can write then that J2, remember J2 is just 1/2 times this. That's going to be equal to then 1/6 times this quantity, sigma 1 minus sigma 2, the quantity squared, plus sigma 2 minus sigma 3, the quantity squared, plus sigma 1 minus sigma 3, the quantity squared. Okay, I hope that looks familiar to you. That is very close to what you're familiar with as the von Mises stress. And in fact, the von Mises stress, so I'll just say recall, the von Mises stress has the same functional form, and in fact we would say that it's actually the von Mises stress squared is equal to 3 times J2, or the second invariant of the deviatoric stress. Okay, and so oftentimes in plasticity, what you'll see is that you'll hear theories called J2 plasticity theories. And so what that really means is that you have a plasticity theory that's based on effectively a von Mises stress. So plasticity theories that are based on the von Mises stress, right, they're called J2 theories. And now you know why. So we're going to come back and revisit this. We're going to talk at a later date about something called the octahedral shear stress. But I just wanted you to show you and link it maybe to something that you've seen maybe in a machine design class or something like that, where you've used the von Mises stress to try to predict the onset of yield in a material. And I just wanted to show you that that is a direct quantity that's linked to the deviatoric stress tensor. That's why it's important. That's why we're going to use it going forward in the class to talk about plasticity theories.